So good afternoon everyone. Now we're going to start with chapter 4, which is something that we already discussed briefly in last lecture in the live session yesterday, but now we're going to cover it in more details. So in chapter 4 we'll talk about something called the gas hydrate, and if you still remember in chapter 3 we talked about the flow assurance. One of the main consideration or the main aspect once you consider processing of natural gas is what we call the assurance of the flow of the gas. And we said that the flow of the gas might be limited or restricted or challenged by several things, such as the precipitation of asphaltene, the waxes, and some other things. And we talked about with a bigging technique where you can remove part of the debris and the waxes and the asphaltene. And we said that one of the most challenges to ensure that the flow of the gas is continuous and there is no issue is the formation of the gas hydrate. So in this chapter, which is chapter 4, we're going to talk about gas hydrate, and we're going to discuss what do we mean by gas hydrate, and we're going to discuss it from the two aspects. One aspect is the thermodynamic point of view, or how it formed thermodynamically, or what is the mechanism or what's the recipe for the natural gas processing. And then we're going to look at it as, because at the end of the day the gas hydrate is also a source of energy in the world. So when we talk about gas hydrate, then we are talking about a structure similar to what you are seeing here on the right side of the slide, which means that you are talking about a situation where water molecules, which is highlighted here, as you can see, these are water molecules, are bonding to each other through something called the hydrogen bond, which is some sort of chemical bonding. And as a result of this formation of the bonding between the water molecules, you will form something called the cage, or space, or vacant space, that I'm going to draw now in let me use different color, purple. So the formation of the chemical bonding between water molecule will form something called the cage, and the cage will be able to entrap certain type of gases, such as, for example, methane. So you can imagine that this water molecules, which is similar to the ice, so once you grab the gas hydrate, it's very similar to the ice. So it's similar to ice, but in fact what's happening that in this crystal you have water molecules that bonding to each other using hydrogen bond, and they form the cage, and the cage will be able to entrap certain gaseous molecules such as CH4, propane, ethane, certain H2S, for example, CO2. So in this chapter we'll learn the mechanism of how they form, and we'll learn the recipe, or the successful recipe, in order to avoid or to get out of the region where you can operate away from the situation or the condition that may cause the formation of the hydrate in your pipes. Now, looking at what we call the gas hydrate, as you can see here in the picture down here, you can see that the gas hydrate is somehow flammable, which means that it can start a fire. You can start a fire simply by giving an ignition source for the gas hydrate, which is similar to the icy crystalline. So the gas hydrate will look like an icy crystalline molecular material, or it's similar to the shape that you are seeing here. So it looks like an ice, or the icy cube, or icy crystalline material, and this icy crystalline material is formed of water, and these water molecules, which can be represented here by the green dots or green circle that I'm going to draw it. These water molecules are bonded to each other through something called, or through a mechanism, or through specific chemical bonding called hydrogen bonding, and as a result these bonding will form something called the cage, which is the cage here. Okay, and the cage will be able to entrap the gas inside it. So this is the gas molecules that's really entrapped inside the crystalline structure of the hydrate. So so when we talk about gas hydrate, we are talking mainly about two things. We are talking about water molecules that are bonded to each other through chemical bonding, and specifically hydrogen bonding, and then we are talking about guest molecule, and the guest molecule, which is entrapped inside the the cage, or the vacant space, is what we called normally will be the gas, which is normally the CH4 or the propane or the ethane, but more specifically, or the common one, is the CH4. Okay, now there is something about the stability of the gas hydrate. When you have minimum number of cavities are filled, which means that, because you need to imagine that these are like, you will have plenty, you have multiple units similar to this unit. So here you have another unit very similar to this unit. It's a replicate of this unit. So you have multiple vacant spaces, or you have multiple cages with different sizes, and we're going to look at these different sizes later on. Okay, based on the structure type that you will form, structure 1, structure 2, or structure H. So when you have a minimum number of cavities are filled with certain gas molecule, this means that you reach a state where the gas hydrate is really stable, which means that it cannot really dissociate easily. You need to provide energy for the gas hydrate, thermal energy specifically, in order to dissociate the gas hydrate and release the gas. And one major thing, one important point to remember, that when you dissociate, or when you reverse the process of gas hydration formation, which means that you are reversing the process, you are dissociating the gas hydrate, you will get two products normally. You will get the gas, and it will be unaltered, which means that if I'm trapping CH4, I will get CH4, and you will get the water molecule, but you need to provide certain amount of energy. In this slide, we will discuss what we call the gas hydrate or the hydrate formation mechanism. So when I'm talking about hydrate in general from now on, it's the gas hydrate. So in this slide, we'll talk about the hydrate formation mechanism. So in order to have a gas hydrate formed, you need two things. First of all, you need what we call the hydrate formation condition, and you need something called the hydrate formation acceleration or promotion, which means that you have a certain condition that contribute or that enhance the formation of the gas hydrate. And as a result, if you have these two conditions together, so this is a successful recipe to form the hydrate, and as a result you will end up in a situation where you have operational problem. The minimum you will get is what we call the blocking of the pipes, similar to what you are seeing here in the picture down, where the gas hydrate formed in large quantities or in large crystal size, and this large crystal size keep growing till it reaches the point where it completely block the pipe. So when we talk about the gas hydrate condition, we are talking about the chemical situation or the recipe that may contribute to the formation of the gas hydrate, such as the presence of free water, and specifically liquid water. And that's why when we get to chapter 6, we will talk about the gas dehydration, why it's important to do the gas dehydration to avoid the formation of the hydrate. So the presence of water as a liquid phase is very important to form the hydrate. But even though the presence of water at the vapor phase also will contribute to the formation of the hydrate, but not as hard as the situation where you have liquid water. The second situation or the second recipe is the high pressure, or the second condition. And the third condition is the low temperature, which means that the moment you are operating at a situation where you have high pressure system, very low temperature, and you have water in the liquid phase, this is a good recipe to form the hydrate. In addition to that, if you have a condition where you are providing agitation, or where your pressure keep changing, or you have what we call the crystal seats or the hydrate seats, this is also another situation where it's gonna improve the situation or the condition, or it will enhance the chance for the hydrate to form. And as a result, once the hydrate forms, you will get something called complete or partially block of the flow line. You will get fouling, you will get erosion, you will get what we call the operational upsets, where you get like flow of the gas issues in the pipes, and this is very critical in natural gas processing. And why it's important to understand the mechanism of gas hydrate, or where to operate in the gas hydrate, because of the situation that in fact when you are operating at natural gas plant, or when you're operating natural gas plant or processing or even pipe or even pumping of the gas, you are always in the domain of high pressure and low temperature. So you're always operating at low temperature and high pressure, which is a favorable situation for the hydrate formation. So it's important to understand the concept or the condition that will lead to the formation of the hydrate in order to avoid that scenario or that condition. To understand this thermodynamically, you need to understand the concept of fugacity. This is something that you have seen before in thermodynamic. So when we talk about the gas hydrate formation, which means that you have what we call equal fugacity, which means that the fugacity of the hydrate is equal to the fugacity of the liquid phase, which is equal to the fugacity of the vapor phase, which is again equal to the fugacity of the ice phase. So you have these four phases together. You have the hydrate, you have the liquid, you have the vapor, and you have the ice, which means that when the hydrate forms, means that the fugacity or the stability of the hydrate depends on the fact that, or count on the fact that, the fugacity of the liquid phase is equal to the fugacity of the hydrate, equal to the fugacity of the vapor phase, equal to the fugacity of the solid or the ice phase as well. And we're gonna see, you don't need really to go more in depth into the thermodynamic of this. You need just to understand that it's once you have the hydrate formation, means that the fugacity or the thermodynamic probability, which is specifically fugacity of the four phases that you have, is gonna be equal. But what you need to understand more is the second few slides, where we talk about the thermodynamic condition, where it's easy to operate or not easy to operate, or where you can avoid the formation of the hydrate. Now, gas hydrate sometimes can be called as, or you can find it in literature as, what we call the clathrate, where the clathrate is any compound where a guest molecule, which is the gaseous molecule, are trapped or entrapped, or are, for example, included in something called a cage, which is what we have seen before, where you have the water molecules simply like this, bonded to each other, and as a result they form the cage. So this is the cage. So again, the hydrate can be thought of as what we call the clathrate, where you have molecules bonded to each other to form a cage, and you have the guest molecule, which is the gas, most probably CH4 for example, will be entrapped in this specific cage. And there are mainly three types of structure when we talk about the gas hydrate. You have structure 1, and we have structure 2, and we have structure H. And in the next few slides we will look at these things. But you need to know, the most important that you need to know, that what type of material or what type of gases can be entrapped in these these structures, sorry. For example, if you are talking about structure 1, normally we are talking about small molecules. Then we are talking about methane, ethane, and carbon dioxide specifically. When we are talking about structure 2, means that you have more large voids, which means that you cannot only include the small size molecules such as CH4 and the carbon dioxide. No, you can also include or entrap in your cage propane, isobutane, and some other natural gas component. Now, moving from structure 2 to structure H, this means that you can also include some other heavier fraction or larger molecules, such as larger than methane, I mean, such as cycloheptane and other compounds. And we're going to see the difference between the three structures, but you don't need really to know what is the drawing of this structure or what is exactly the number of molecules, for example. All you need to know is that they are different in terms of the cavities, or in terms of cages, or in terms of the type of the gases that can be included. And you need to understand one fact, that when you are talking about natural gas processing, the most common gas hydrate structure that can be found is what we call structure 2. Now, speaking of these type of structure, where we're going to discuss them in details. Now, when we talk about structure 1, for example, structure 1 means that you have approximately 46 water molecules, okay, and these water molecules are bonding to each other to form or to give you 8 voids approximately, okay. 2 of these voids are what we call the pentagonal dodecahedra, okay, and the remaining 6 cages will be smaller in their size, which means that you can use these 6 voids, for example, to accommodate the small molecules. Now, when we talk about structure 1, having, for example, having 8 voids, 2 of them you can consider these 2 large, and 6 approximately you can think of it small, which means that I can entrap mainly methane gases in the 6 cages that you have, and also methane can also be entrapped in the 2 large, or what we call the 2 pentagonal one. But also you can also entrap the ethane as well. So if you have methane only, the methane will be entrapped in most of them, but it will be very hard to entrap the methane in the large voids. But if you have a mixture of gases, and this is gonna be another thing that we're gonna discuss, if you have a mixture of gases, let's say that you have methane and ethane, the ethane will be easily trapped in the large voids, and methane will be easily trapped into the small voids or cages. Now, one more thing to know about the structure one, that larger molecules such as propane cannot really accommodate in structure one, or cannot be entrapped in structure one. So propane cannot be really entrapped in structure one. So that's why this is like a hint for you to understand why structure 2 will be more suitable, or more adjusted, or more accommodation, or more preference once we talk about a natural gas complex. Now, when we talk about structure 2, you have approximately 136 water molecules, and these 136 water molecules, they form, or they give you approximately 16 small voids and 8 large voids, which means that it can accommodate wider range of material. The larger voids will be entrapped, or will be used to entrap, for example, propane, N-butane, and azobutane. And the small molecules will be used to entrap the methane and the ethane as well. Sorry. Now, for the last structure, which is structure H, in structure H, you will have 3 different cavity sizes. You will have very small cavity size, which is very similar to structure 1, which means that you can accommodate CH4 and ethane, CH4 specifically. And you have the largest cavity size, which can accommodate larger molecules such as benzene and cyclopentane. Other thing to keep in mind, that as we explained earlier, that natural gas will form structure or gas hydrate based on structure 2 hydrate more than any other thing. So it's well accepted, or it's well documented in the literature, that normally structure 2 will be found in natural gas hydrate. And another thing to keep in mind is that the type of the hydrate that forms depends on the guest molecule, and the solubility of the hydrate will govern what we call the rate of formation of the gas hydrate. So here we are talking about 2 different things. So the type of the hydrate that's gonna form based specifically or more in the guest molecule, but the rate of the formation will depends on the solubility of that gas hydrate as well. Now, another thing that we need to discuss is the formation of the gas hydrate for pure substances and mixture. But before that, let's look at this example. You have the idea that, let me just draw this sketch. So now I need to this scenario. I have CH4. This is the cage. What I'm drawing in green now is the cage. So I have 2 cage that has the same size, and in this two size I have, for example, propane molecule. So this is like propane. And on the other side I have CH4, for example, which is, I'm going to draw in red. Okay, this is CH4. Okay, so now theoretically, or even experimentally, it was found that to form a hydrate using the propane alone is much easier than forming the hydrate using CH4, despite the fact that CH4 has more solubility in water than the propane, which means that the solubility is not the only parameter. So here the question is that CH4 is more soluble in water than propane, but propane will form the hydrate much easier than the CH4, or will require less pressure than the CH4. The CH4 will require more pressure to form the hydrate once compared to the propane. And the reason for that is the size of the molecule, because CH4 is small in molecule, is a smaller molecule. So once it gets into the cage, it will keep moving to another location, to another location, to another location, which means that you will require high pressure in order to entrap or to stabilize that CH4 molecule inside the cage. But when we look at the case of the propane is large enough, so once it gets inside the cage, it will be stabilized directly because of the steric effect or the size effect of the molecule. This means that propane is larger molecule, it can be entrapped easier, and it will require less pressure. Another thing to keep in mind about the hydrogen sulfide. The hydrogen sulfide will normally form, the hydrogen sulfide is highly soluble also in water, more than methane, and it's larger molecule than methane. This means that it will require less amount of energy or less amount of pressure to form the hydrate. So which means that H2S will also form, or the mechanism or the rate of formation for H2S will form sorry, will form the hydrate much faster than the methane or CH4. Another few points about the gas hydrate formation is about the heavier fraction. Now we're going to talk about, for example, normal butane. Normal butane normally will form the hydrate, but this hydrate is very unstable, which means that it can dissociate easily. Therefore, we can accept the fact that all paraffins larger than butane are non-hydrate formers, so they will not form the hydrates. All paraffins larger than the butane. So for natural gas, another fact is that for natural gas mixture, if you have natural gas mixture, you will form the hydrate much faster or much easier than if you have, for example, CH4 alone. So normally, if you have pure component or pure substances, being CH4, being ethane, being propane, and you have a mixture of gases, the mixture of gases will form the hydrate and will stabilize the hydrate much faster or at lower pressure compared to the pure substances. And the reason for that the gas hydrate, as we explained, it has like wide variety of cages. So if you have natural gas mixture, means that you have smaller molecules such as CH4, CO2, H2S, and you have larger molecules such as propane and butane. So when you have the natural gas mixture, you can stabilize the hydrate, or you can form the hydrate much faster, because these small size and large size variety will stabilize or will occupy the cages quickly. Meanwhile, if you have only CH4, this means that the CH4 will go and only occupy the small size, and it will keep moving inside these small cages. This means that you need to apply more pressure in order to push or to force the CH4 molecule to be entrapped inside that cage. Now the gas hydrate also, or the crystal hydrate, can form also in the absence of water if you don't have liquid water, but in this case the hydrate size will be much smaller. In case you have for example water molecule, the hydrate formation will be much easier, and the growth rate for the hydrate will be much faster. So the presence of liquid water will promote the formation of large crystal size, or will promote the growth of the gas hydrate in larger size. Meanwhile, the absence of the water molecule in liquid phase will also allow the formation. If you have only slight amount of liquid water, if you have no liquid water, only you have the vapor phase, you will again form the gas hydrate, but it will be in smaller size. Another few facts about gas hydrate is the fact that, for example, as we mentioned earlier, the gas hydrate is formed of water and gas. But you can think of the fact that the water molecule will give or will contribute to around 90% of the mass of the gas hydrate. So if you have a gas hydrate that weighs, for example, 1 gram, 90% of this 1 gram will be basically water, and the 10% will be the gas. And the second point that you need to keep in mind, that the gas hydrate formation and dissociation is reversible process, which means that if you have a recipe, if you have water plus gas or the guest to form hydrate, this process is reversible. You can still dissociate, or you can still degrade or dissociate this hydrate to form gas and water, or to release gas and water. And as I mentioned earlier, the gas and the water will be released unaltered or unchanged. So it will be CH4 and it will be, for example, water. Therefore, the process of formation of the gas hydrate and dissociation of the gas hydrate from chemical or from reaction point of view is a reversible process. And heat of dissociation is between 450 to 500 kilojoule per kilogram, which means that you will require, for each 1 kilogram, you need to provide around 500 kilojoule of heat or energy in order to dissociate the hydrate and form or release the gas and the water. Now we're going to try to look at something called the gas hydrate formation condition, or the parameters or the condition that will contribute to the gas hydrate. And then this means that we're going to look at something called the gas hydrate formation curve. And this is something that we're going to discuss in the next few slides. So please make sure you understand the concept here. So when we talk about the operating condition to avoid the gas hydration or the gas hydrate formation, we are talking about something called the gas hydrate formation curve, which will define or will give you an idea about the operating temperature and operating pressure range. So you are talking about operating temperature or operating pressure range that you need to operate at sub-C, for example, or under a specific condition at steady state in order to avoid the formation of the natural gas. And when we talk about the gas hydrate formation curve, we are referring to something similar to this curve that you can see here at the low side of the slide. And this, for example, this chart or this figure, which is the hydrate formation curve, will give you an idea about the stability of natural gas hydrate as a function of two things: pressure and temperature. Which means I'm going to explain it later on. Which means that you can use this chart here. I'm going to just use different color. You can use this chart here to read the pressure value and temperature value. Temperature is the x-axis and pressure is the y-axis, and based on that values you can specify whether you are operating at a situation where you're gonna obtain or you're gonna get gas or the hydrate formation, or no, you are safe or you are away from the hydrate formation region. So to the right of the dissociation curve, which is here, this is what we call the dissociation curve. I'm gonna just use different color. Let me just use the yellow. Here is something called the dissociation curve, and here is something we call the hydrate formation curve. So when you operate in this region, let's say that you have the pressure value here around 100. Oh, sorry, the temperature is, let's say, imagine that this is 100 Fahrenheit. Imagine. And the pressure is approximately, let's say, 50 psi. These are not accurate value, by the way. This is just imagination, just to demonstrate. So imagine that you have a value of 50 psi and temperature 100 Fahrenheit. This means that in this condition, since you are to the right of the hydrate dissociation curve, this means that you will not form the hydrate. But imagine you are at the same temperature, at the same pressure, 50 psi, and the temperature was found to be, for example, 10 Fahrenheit, let's say. So you are here. This means at this condition you are to the left of the what we call the hydrate formation curve, which means that if you are operating at this area, the hydrate will form for sure. So this is how you can use the hydrate formation curve to define the operating temperature and pressure, or what we call the temperature and pressure envelope, in which you need to operate in order to avoid the formation of the hydrate. And as you can see, the stability of the hydrate increases with two conditions. Let me just take another color. As you can see here, the moment you increase the pressure and you reduce the temperature, this is very favorable situation for hydrate to form. This is very suitable condition for the hydrate to form at high pressure and very low temperature. And again, as I mentioned earlier, this is the condition where you're gonna operate at when you are dealing with natural gas. So far we have explained what we mean by the hydrate formation curve, but now I'm going to explain the last thing, which is something called the metastable region. But before we start to talk about the metastable region, we're going to talk about something called the subcooling of a system, where subcooling of a system is defined as the difference between the hydrate stability temperature, this is one, and the actual operating temperature, but it has to be at the same pressure. So when we are talking about subcooling of a system, we are talking about two things. We are talking about the difference between the hydrate stability temperature and the actual operating temperature, but both has to be at the same pressure. Now, if you have a system, for example, that operates at 40 Fahrenheit and the pressure is 3000 psi, and the hydrate dissociation temperature is around 70 Fahrenheit. This means that the system is experiencing around 30 Fahrenheit of what we call the subcooling. Okay, and during this period, or during this 30 Fahrenheit of subcooling, which is the difference between the hydrate stability temperature and the actual operating Sorry. Now, the subcooling of a system without the formation of further hydrate, this means that you have the area between two things, between the hydrate formation curve and the hydrate dissociation curve. And the difference between the two is what we call the metastable region, which means that you are cooling the system further, you are further cooling the system, but in fact you are not forming more of the hydrate, which means that you reach the maximum capability of the hydrate to be formed, or the maximum condition, or you reach something called like a saturation for the hydrate formation to happen, which means that if you subcool the system further and further, this means that you will not get more, for example, of the hydrate formation. You will not get more of the hydrate formation, and this subcooling without hydrate formation leads to the area between the, or the difference between the hydrate formation curve and the hydrate dissociation curve, which is called the metastable region, where the hydrate, in fact, in this region, let me just, so during this region, the hydrate is not stable, which means that it can dissociate easily. Now let's look at this chart where it describes the hydrate formation condition or situation for certain component. You have the methane, you have the CO2, ethane, propane, H2S, and IC4, which is isoputane, and normal butane, which is NC4. And as we explained earlier, the hydrate formation curve is, you have the temperature on the x-axis and you have the pressure on the y-axis, and you have these characteristics curve for certain component. Let's look at, for example, the methane. If you look at the methane here, for example, here is the, let me just use different color. For example, here is the curve for the methane formation, which means that if I'm operating at any point above this curve here, for methane only, this means that the gas will form. So if you have a temperature of 500 degrees Celsius, for example, sorry, not 500. If you have temperature of 5 degrees Celsius and you have the pressure is equal to, for example, 1 megapascal, and you have the gas which is CH4, therefore the hydrate will not form in this condition. So if you have the temperature at 5 degrees Celsius, you need the pressure to be at least between, like, let's say 5, you need at least 5 megapascal for the hydrate to form if you have CH4. Now if you have another component, let's look at H2S. Let me just use different color. Now let's look at H2S, for example. This is the H2S line, and we can explain what do you mean by the vertical one later on. So this is the H2S. So for the H2S, if you have 5 degrees Celsius and you have only 0.1 megapascal, this means that the gas hydrate will not form. But if you have, let's say, 5 degrees Celsius and you have approximately 0.1, or actually let's say it's around 0.3 almost here. So if you have the pressure of 0.3 megapascal and you have the temperature of 5 degrees Celsius, and if you have only H2S, the hydrate will form. So anything in this region for H2S will form the hydrate, which means that H2S will require less pressure to form hydrate once compared to the methane, which means that H2S is much easier to form hydrate once compared to methane. And you can see this vertical line that you can see it here in some of the and you can see also here some of the lines, or the vertical lines that you can see here. These are the situation, or these are the condition when you have the hydrate formation curve intersect or hits the vapor pressure curve for that specific component. So this justifies why do you have vertical line. So the vertical line will take place at the point where the hydrate formation curve will hit the vapor pressure curve for that specific component. Here in this slide that we will see also that similar trend to what we have seen before in terms of hydrate formation curve is reported by Carroll as well in this chart, where you can see that the hydrogen sulfide, for example, this is the curve, for example, for the hydrogen sulfide, and for example this is the methane, which is very similar to what we have seen before in the other chart or the other curve, but this is like developed by Carroll. So this is again an idea about what we call the hydrate formation curve, which specify the region similar to what we have learned, specify the regions, for example, where hydrate formation will take place or where hydrate formation will not take place. For example, if we are referring to hydrogen sulfide, then this means that if you are operating at this condition, any point at this region, then we are safe to say that there is no hydrate formation. And if you are operating in at this zone, for example, the one that I'm gonna highlight now in yellow, this means that the hydrate formation will take place. Anything in this region. Okay. Now let's have a look at this hydrate equilibrium formation curve for propane and water system. What you can see here, the x-axis is the temperature as well, and the y-axis is the pressure. And you can see here we have two lines. We have first line, which is the blue line, is what we call the vapor pressure curve. So this is the vapor pressure curve, and this is the hydrate formation curve that I'm going to draw now in, let's say, in green. This is the hydrate formation curve, and as you can see here, once the hydrate formation curve touch or hit the vapor pressure curve, the hydrate formation curve will go vertically, and this is well-known phenomena in most of the hydrate formation curve equilibrium. So now if you look at the point where temperature equal to approximately 0 Celsius, which is this line, for example, if we split the curve into regions, if you look at this point at 0 degrees Celsius, you will find that the hydrate and ice are present at this region. So in this region you have mainly hydrate and ice, and in this region you have vapor and ice in this region. So on top of the curve, which is this region that I'm gonna now highlight it in yellow, so now I'm talking about this region. So we are talking about the point 0 degrees Celsius and above the hydrate curve. So we are talking about this region specifically. You have hydrate and ice in this region, and below the hydrate curve you will find the vapor and ice. When we are operating at temperature less than, if T less than 0 Celsius. Okay. Now if temperature is greater than 0 Celsius, let's take another blue color, for example. If you are operating at temperature greater than 0 Celsius, or with the freezing point, for example, you will find that hydrate is the only solid phase that can be found in this region. For example, you will have hydrate and water, but hydrate will be the only solid phase that can be found in this region specifically. And below the hydrate curve you can find that you have no hydrate phase, you have mainly vapor and water in this region below the hydrate formation curve. And as we mentioned, at the intersection between the hydrate formation curve and the vapor pressure, you will see that the hydrate formation curve will go vertically, which means that this is the maximum hydrate forming temperature, which means that at this point this is the maximum temperature or the maximum hydrate forming temperature for this pure substances or for this pure component, which is specifically in this case propane. Now we will learn certain techniques that can be used to find the what we call the estimate the hydrate temperature for specific gas, where we are talking in this chart, or in this case more specifically about sweet gas. that you know exactly how much is the relative density of this sweet gas, for example. Okay, so you can use this chart, which is based or which is obtained from a GBSA book, engineering data book, which is chart or figure 2019. And these like charts are used for specifically for estimation purposes, not for design purposes, because this is considered as what we call hydrate prediction correlation or hydrate prediction charts, which is empirical charts for sweet gas, and this is specifically for sweet gas. So you can have on the x-axis you have the temperature to be approximately in the Celsius and the pressure to be in the kilopascal on the y-axis, and you can get it for different gases based on their relative density, for example. And as I mentioned earlier, this will give you not exact number or value for the temperature. It will give you an approximated temperature that you can use mainly for prediction, not for design purposes. Another interpretation for the curve that you have seen before, where you can predict the gas hydrate formation from the specific gravity of the gas, is what we call the Cat's gas gravity method, which is very similar to the one that you have seen before. In fact, it's the same one. Here we are just seeing the the chart in different formula, where you can see the pressure in PSIA absolute and the temperature in Fahrenheit, and you can use this mathematical formula to calculate how much is the temperature of the hydrate formation if you know the pressure and if you know the specific gravity of the gas that you have. But you need to keep in mind that this chart normally is applicable if you have your gas mixture or the relative the specific gravity of the gas that you are using is less than 0.7 or at least maximum 0.7. If you are in the 0.8, 0.9 or 1, then the correlation or this chart will give you a large error or high error. This means that you cannot really count on these charts, empirical charts, to calculate, for example, the hydrate formation condition for non-sweet gas and the one that has, for example, specific gravity more than 0.7 as well. And again, it should be used mainly for first prediction, similar to the chart that we have explained. In fact, this chart and the chart before are the same, except that you are using different units for the pressure and the temperature. So you can use it again for prediction purposes, not for design purposes. For design purposes, you need to modify it, or you need to use other methods that can give you more precise data. Another empirical charts or another empirical technique that's used to predict the hydrate formation condition is based on what we call the allowable expansion of gases without hydrate formation concept, which means that you are allowing the gas to move from one condition to another condition, or to expand from a specific pressure and temperature to another specific pressure and temperature without having what we call the hydrate formation. And this like will be represented in this class as two figures, figure 2021 in the GPSA textbook and figure 2020. The difference between the two, that figure 2020 will represent for specific gravity of 0.7, 2021 will represent the expansion or what we call the expansion, allowable expansion of gas without hydrate formation for what we call the gas that has specific gravity of 0.7 approximately. And we're going to see one illustration, one specific example where we describe how to use these charts. But this chart in general describe what we call the final pressure in the x-axis, and the y-axis will have the what we call the initial pressure, and here you have the different range of temperature that you can talk about 170, for example, Fahrenheit. You can talk about 180, 110, 100. These charts represent different temperature, and based on that we're going to see, for example, if we are allowing the gas to expand from specific pressure and specific temperature to another specific pressure and temperature, will hydrate form or not. And we will see this in more details in the next two slides. Now we're going to look at this example where we're going to illustrate the use of what we call the expansion or the allowable expansion or the gas expansion parameter, or the gas expansion concept, or what we call the permissible expansion for a gas without having or without forming what we call the hydrate. Now in this example we have a gas, and this gas has a relative density of 0.6, which means that we're going to use figure 2020 because it's for specific gravity of 0.6. Okay, and the gas has a molecular weight of 17.38, and the initial pressure for the gas was found to be 25,000 kilopascal. Now this means that I will start, so this is like initial condition, so this is initial condition 25. So I will go like in the chart has, as we explained earlier, the chart has in the x-axis you have the final pressure, or the final, or the second stage, or the second the pressure at the second stage, and you have at the y-axis you have the initial pressure. So initially I have it at 25,000 kilopascal, so which means that my initial condition is this condition, which is I'm drawing here in red color. Okay, so this means that if the initial temperature of the gas was 70 degrees Celsius, so I'm gonna look at where is the 70 degrees Celsius. I'm gonna draw it now in let me choose the color. So this is the 70 degrees Celsius, this is the 70 degrees Fahrenheit. Okay, okay, and I'm taking the 25,000, so which is the red line, so I'm taking the intersection between the two, which is this point, and I'm gonna go down all the way to the point where I'm gonna read what will be the final pressure. So the final pressure will be around 3,000 kilopascal absolute, which means that if my gas is initially at 25,000 kilopascal and the temperature is 70 Fahrenheit, this means that I can easily expand the gas up to the point where I can get the pressure to 3,000 kilopascal, which means that I'm going to reduce the pressure up to 3,000 kilopascal without having the hydrate formation. Now look at the scenario from the other side. If the initial temperature is 55 degrees Celsius, so I'm going to draw another line now. I'm going to look at the 55 degrees Celsius. So here is the 55 degrees Fahrenheit, sorry. So here is the 55 Fahrenheit. So I'm going to draw this line again, and I'm going to take it this way, sorry. Okay, and I'm going to take the intersection with the red line, which is the initial condition of 25,000 kilopascal, and I'm going to go vertically down all the way till I reach approximately 8,000 kilopascal, which means that if my gas is initially at 25,000 kilopascal and 55 degrees Celsius, in this case, for example, sorry, I mentioned Fahrenheit, but in fact this chart deals with the Celsius. So please correct this all over the slide presentation or explanation of this slide specifically. So I use the Fahrenheit, but in fact the temperature is in Celsius. Okay, so this means that if I have initial condition, let me just summarize here. If I have my initial condition at 25,000 kilopascal absolute and temperature of 70 degrees Celsius, I can simply allow my gas to expand up to the point where I have the pressure equal to 3,000 kilopascal, guaranteeing that there will be no hydrate formation. Now, if my initial condition is 25,000, which is the second case, if I have 25,000 kilopascal absolute again, and the temperature is 55 degrees Celsius, this means that I can reduce the pressure up to 8,000 almost, kilopascal without forming or without having any issue with the formation of the hydrate, which means that I can go all the way down to 8,000 kilopascal without having any hydrate formation. So let's have a look at this example. This is another good example on where to use or how to use the what we call the permissible expansion for the gas. Sorry. So you have a gas that has specific gravity of approximately 0.6, and the gas has initial condition of 21 psi and 110 Fahrenheit, and this is at the wellhead point, and the gas will go from the wellhead point to a separator, and once it enters the separator, the pressure will be reduced to approximately 700 psi. So now we need to decide or to look at whether you're gonna get what we call the hydrate formation or not. So I'm gonna take
simply I'm gonna follow the steps, which is I'm gonna go from the initial condition, where the initial condition will take you from the 21 psi absolute, which is this line that you can see here in red, and I'm gonna give it green color, for example. Okay, and the temperature of the gas at the wellhead is 110. So I'm gonna look at the 110. Where is the 110? And I'm gonna draw a line also for the 110 Fahrenheit. And you have to keep in mind that this is a slightly different chart. Here we are dealing with Fahrenheit in terms of temperature, and the pressure is psi, not kilopascal, similar to the previous one. So so we're gonna take the intersection. Now I have the initial condition, which is 2100 psi and 110 Fahrenheit. So I have now the initial condition for the gas. So which means that if I go vertically down all the way, I will find what will be the pressure that I need to expand my gas to. And I found that the pressure that I need to expand my gas to is approximately 850 psi. And my separator is operating at 700 psi, which means that I'm operating here. Okay, and this means in fact that the hydrate will form, since I'm operating at pressure less than the maximum expansion pressure for the gas. This means that the hydrate will form if I'm expanding the gas from the 2100 to 700 psi. If I'm expanding the gas from 2100 to 850 psi, the gas hydrate or the hydrate will not form. Since my separator goes to 700 psi, this means that my system will witness or will experience what we call the hydrate formation. So I hope it's clear. This demonstration now is clear for you.